Oh, all right. Welcome to DOE's pre-implant training webinar on process heating systems and DOE's PASS tool, process heating assessment and survey tool. Good afternoon and good morning for some people. Basically, thank you for joining today's webinar. And this is, as I mentioned, this is pre-training webinar for our process heating training in Saukville, Wisconsin, between January 19 and 2022. So we will have this training, on-site training. So to prepare all participants for that training, we have organized this particular webinar. I am Sachin Nimbalkar, currently working as a R&D staff at Oak Ridge National Laboratory. Actually, ORNL is US DOE's national lab, and I'm actually a technical account manager for DOE's Better Plants program. This program is around since 2010, and I provide a technical support to DOE's Better Plants program partners. For example, Charter Steel is a DOE's Better Plants partner, and there are 160 other companies. So I actually provide technical support through energy roadmap development, baselining analysis, implant trainings, field visits, to investigate feasible measures to reduce process energy requirements. And so today's webinar, we are going to focus on process heating equipment. And Arvind is actually, Dr. Arvind, he is actually going to discuss process heating equipment, as well as how process heating assessments are done, and then how process heating assessment and survey tools helps you to identify energy efficiency opportunities. So at the same time, we have Mr. David Mowry from Saukville, Wisconsin, and then Terry Emerson is also going to join in next few minutes. So they are providing us technical support. They are working with local team at Saukville, Wisconsin plant, and they are providing us data related to process heating equipment. So with that, I will go ahead and turn it over to Dr. Arvind Thekdi. Arvind, if you don't mind, please start with your introduction, and then I will actually change slides for you.
Okay, thanks, Sachin. My name is Arvind Thekdi, and I am one of the developers of some of the training material that we are going to use. Before I start, I have to give one disclaimer, I guess, in a way. I have some cough, and my throat conditions are not exactly 100% correct. So I may have to stop either for a gulp of water or cough or something. So my apologies for this kind of disturbances. Anyway, my background is in process heating. I have worked in this area since 1970. So that makes me very old and experienced, I guess. I work with many furnace companies. I have my own company, which is called E3M. And we provide training services as well as tools development and the actual on-site assessments. I've been doing this thing, oh God knows what, 1999 or something, and probably have visited 100 or so plants throughout the world. Steel industry is one of my favorite industry because the company that I used to work for, and I'm sure you know the name, it's called Surface Combustion. This is where I was in charge of R&D, design, and so on and so forth. So I've been to many steel plants, and that helps a lot in identifying energy saving opportunities, as well as discussing what can be done economically justifiable. So this is a little bit of my background, as you can see, and MBA, PhD, Masters, BE, couple of furnace companies, Lee Wilson, Ipsen, surface combustion, so on and so forth. Next slide, Sachin. So we are going to start with this. We have total 1.5 hours. So I like to go for about 45 minutes or so. And one thing, I know you are in silence mode. So if you have any question, as Sachin has said here, type your questions and we could discuss those in the middle of the presentation or preferably at the end of my presentation. So let's start with saying what is process heating. It's basically anything or any kind of process where we supply heat to different types of materials. And there are many different names for this kind of equipment. Furnaces is probably one of the most commonly recognized name in steel industry. Then there are ovens and heaters and thermal oxidizers and of course boilers and so on and so forth. Most important thing really is that in each of these equipment, we use heat to do something to some sort of material. So for example, in arc furnaces, we melt the metal. In reheat furnaces, we reheat the metal, so on and so forth. Next slide, Sachin. Next, Sachin. Yeah. As you know, there are many, many different types of equipment which people use in their manufacturing operations, in manufacturing plants. They could be classified in many different ways, but the Department of Energy has selected to do it in the way that I have shown here. One is what's called process heating and steam systems, which includes furnaces, ovens, boilers, so on and so forth. The second one is the electrical motor systems, which is everything that you use with electric motors, with the exception of pumping systems and compressed air system. And then there are other type of HVAC, lighting, so on and so forth. Obviously, in a plant, the most visible thing is lighting. But if you look at it, you say it's going to be less than 2% of your total energy use is going to be in lighting. The important part is that if you come back to process heating, anywhere between 60 to 80% of the total energy or energy bills that a company pays is 60 to 80% or so. And it's a lot more in steel industry than some of the other industries or so, because the steel industry or the steel plant uses a lot of gas and electricity both. So 60 to 80% could go there. And then the saving opportunities, as you can see at the bottom, 10 to 30% for furnaces, 5 to 10% for electric motors, 10 to 20% for pumping, 10 to 20% for compressed air, and 5 to 10% or so. The basic message here is that process heating is extremely expensive and it uses a lot of resources, and this is where most of the opportunities lie. Next slide, please. So there are many different types of process heating systems people use. Most common one, which is certainly in the steel industry, is the two types. One is the fuel-fired systems, where gas, certainly in the United States, gas is used for combustion and supplying heat. Second one is electrically heated systems. And since you are working for a mini mill, you all know that the electric arc furnace uses lots and lots and globs of electrical energy. So the fuels and electricity are the two major sources for EAF kind of plant. For integrated plants, steam is also one of the important source of energy, and steam is extensively used. But for our purpose, we'll concentrate on fuel-fired furnaces and electrically heated systems. Next, please. Next, Sachin. Yeah. So let's take a look at the fuel-fired heating system. In this case, the heat is generated by using solid, liquid, or gaseous fuel. We in the United States are very fortunate that we don't have to use solid fuels like coal or wood and liquid fuels like fuel oil and so on and so forth, because we have plenty of clean natural gas, and most processes that you have, I guess almost all other than electric arc furnace, uses natural gas. And then once you burn it, it gives up the heat and you transfer the heat to the material. The combustion gases can be directly in contact with the material, which is direct heating, as in the case of reheat furnaces, or it could be confined in a separate source, such as radiant tube that you have in your annealing furnaces. That's what they call indirect heating. So there's a direct heating and indirect heating. Many different types of fuel-based systems we talked about. Approximately 65% of the total energy, process heating energy, used in US is by fuel-fired systems. So a huge amount of energy is being used as fuel. Next, Sachin. Let's take a look at, there are many different types of furnaces. One most common that you see in your plant is a continuous direct fire furnace, which is the reheat furnace. And in this case, you see a bunch of burners above and below the hearth level. They fire it, the gases come in contact with steel. The good thing is they hit the material. The bad thing is they oxidize the material, because the flue gases have carbon dioxide and water vapor and some oxygen in it, and that at high temperature oxidizes the steel. So there are pluses and minuses to that. Next, Sachin. The other one is the batch type of direct fired furnaces, where you have material going in the furnace, you load the furnace, close the door, and you start your burners. And the burners would come, the flue gases would come in contact with material being heated. In this case, it happens to be a bunch of coils being heated, so on and so forth. But batch, because the material is not going in and out continuously. Next slide, Sachin. These are some of the indirect heating systems, or radiant tube. Most common one is the radiant tube, and many of you have seen radiant tubes where you have anywhere between 4 to 8 inch diameter high temperature alloy tube. We fire the burner in the tube, the hot gases would hit the radiant tube, and then they will radiate the heat. That's why it's called radiant tube. Since it's radiation and is a local source of heat, we need to distribute the heat. So in many cases, you will have a fan which circulates the gases. And there are many different ways of installing fans. The most common one that you see is in your batch annealing systems or in your annealing furnaces. The other one is the where you have a retort or an inner cover, if you want to call it, where you fire the burners outside the cover or retort. The retort gets hot, and then it transfers its heat to circulating gases, which in turn heats the material. So that's another type of heating system. Next, Sachin. As far as the steel industry is concerned, and particularly the mini mill or your kind of shops, what are the major process heating equipment? Electric arc furnace obviously is very large. The next slide is in the melt shop, you have few ladles. So ladle heating uses gas, and then there are tundish heating also. So as far as the melt shop is concerned, at the arc furnaces, usually they have oxy fuel burners, in this case oxy gas burners. then we have tundish, and we have ladle heating. Then the next one, which you see on the bottom left side, a reheat furnace, which uses lots and lots of energy, hundreds of millions of BTUs of energy to heat the material. It could be the slab, or it could be billet, or it could be bloom, whatever it is there. The next to that is an annealing furnace. This is commonly used as the stack annealing or batch annealing furnaces there. And then next to that, you see a commonly used heat treat furnace for annealing the material or tempering or hardening or so on and so forth. This could be mostly radiant tube fired furnace. Above that is a continuous annealing furnace. The top right side is a continuous annealing furnace, where again people use combination of radiant tubes and direct fire. But these are the commonly used things. Next slide, go ahead, Sachin. This shows a schematic which all of you know very well. I don't have to explain to you. We have electric arc furnace, we have refining, we have continuous casting. This casting then produces slabs, then it goes to slabs or blooms or thing. And then from reheat furnace, we go to many different types of finishing operations. In your case, I guess it's wires. So you go to the bottom one, you go to the rolling mill, and you produce bars and rods and so on and so forth. But there are many different types of shapes and sizes, and in many cases, there are some downstream operations, such as annealing. There may be hardening, there may be carbidizing, there may be tempering. Many different types of finishing operations are going on where the gas or the fuel is being used. Next slide, Sachin. So, we say that there are many different types of furnaces, and that's a problem. Why is it a problem? It's a problem because people think that whatever furnace they have, it's unique to them. It's just like having our kids. They're all unique to us. They may be very similar to the neighbor's kids, but they are very special. So everybody thought that furnaces are unique to them, ovens are unique to them. So about 16 years ago, DOE convened a meeting of all kind of people associated with furnaces, the furnace suppliers, the consulting companies, the steel companies, so on and so forth, and say, look guys, we got to come up with some common description of a heating system. And that's what they came up with, which is pretty good actually. So starting with the left side, two things are happening. Two things are going in the furnace. One is the energy, in this case, very likely gas. And the other one is the material that we are trying to heat. So think about a reheat furnace and say you got a burners. So we're putting fuels in the burners, and then we have either walking beam or pusher or whatever it is throwing the slabs in the furnace. Close the door. Then what happens to that fuel is it makes heat. So the burners themselves don't do much. The gas itself doesn't do any heating. It has to be burned in the form of a flame. So you kind of get a flame and the hot gases. And those hot gases then would transfer the heat to the material that's being heated, in this particular case, slabs. The burners could be top fired, bottom fired, they could be high velocity, they could be flat flame burners, they could be whatever, different types of it. But in each case, you got a whole bunch of hot gases at 3,000 degree or 4,000 degree Fahrenheit, and those gases then would hit the material so that it comes out at the other end at say 2200 degree or 2250 or whatever temperature you want. So the job is done. And yet you have to deal with something else, which is Now you have the exhaust gases coming out. In some cases, we will have to recover the heat, as in reed furnaces, we have recuperators there. And then in some cases, we'll have to put some sort of emission control system because there are restrictions on what you throw out in the air. And a prime example is what's going on in the arc furnaces, where we have a whole bunch of bag houses or electric static precipitators to get rid of the dust and so on and so forth. This is good, but all this needs to have a controlled temperature enclosure, and this is what we call a brick box or a furnace. And so that's what we call the heat containment. Now, in addition to that, there may be a few little things going on in here. Sometimes we have to use the process atmosphere. Could be hydrogen, could be RX gas, could be TX gas, whatever it is, to make sure that the work is protected. And then that atmosphere has to go out. In addition to that, we'll have sensors. We have different types of materials, design tools, so on and so forth. There could be other things like water cooling, as in case of walking beam furnaces, other type of cooling, so on and so forth. So this kind of gives generic description, and the reason why this is helpful is that now we can take each of these elements of a furnace and look at it and see what can we do to reduce the energy use. So for example, in heat containment, how can we reduce the wall losses, opening losses? In heat recovery, how can we get more heat recovery? So on and so forth. Next slide, please. This is another way to look at the same diagram in a more realistic way. So we divide these again into 10 different components. Number one is the material that goes in. You could do something to material to reduce the energy use. There could be material handling system. The third one is the burners themselves. We could do something to the burners. The fourth one is the exhaust gases. We could do something to them to reduce the energy. Then furnace walls. The sixth one is the openings and doors and stuff like that. Seventh is going to be the water cooling, particularly in walking beam furnaces. We have water cooled skids. And then control system. People use level 1 control, level 2 control, level 3 control, so on and so forth. And then you have blowers and exhaust air blowers or combustion air blowers, and then there are a whole bunch of other heat losses. So again, what we are going to do here in discussion as well as in practice, we are going to look at each of these elements and see where we can save energy. Next, Sachin, yeah. So what do? First, we do energy distribution. We got to find out where we are, how much energy is used, and where it is going. And this is where most of the time that we will spend in the plant is going to be to find out where energy is used and how much energy is used. And we're trying to cover all these 10 elements. In most cases, we end up covering maybe 4 or 5 or 6. Because some of them are difficult, some of them are not existing, so on and so forth. So, the very first thing we do is look at the energy distribution and see where the energy is going. Then we look at the areas where energy losses are taking place. And then next thing we do is estimate the energy loss. We make some measurements. We have bunch of instruments that we will see. We collect the data and we analyze by using some of the tools that Sachin will discuss, and we can find out how much energy is being lost in each of these 10 or 5 or 6 components there. Then we look at it and say, oh my God, this is how much energy is going where. Now what can we do? What is practical to reduce this energy loss or recover part of the energy. And if we select 6 things that we think we can do, then we got to find out how much energy can we save. In some cases, we can save 1%, and in some cases, we can save 25%. Obviously, we are going to go after the one which gives the most bang for our bucks. So we select those, we find out those, and then we look at those and have sort of discussions, say, are these practical things? Will they have any other problems if we do something? Is it going to screw up something else? Will this be cost effective? So on and so forth. And then based on that, we select what we can do and what we should do. Because ultimately, the people who control the money, the people who control the final decisions are going to look at the cost effectiveness and say, is it worth doing, not only from cost point of view, but from safety point of view, from government regulations point of view, so on and so forth. So this is the methodology, these are the steps that we use in this plant assessment that we are going to go through. Then, as we said, we need to get the data collection. We have to collect the data, and then we have to note down that data. So there are some data collection forms, and it says yes, no, but that's okay. This is what we do. Sachin would show you the data collection forms also and see what kind of data is required. Next slide, Sachin. So, well, I'm going to show you. Sorry. These are the data collection forms. I guess I'm going to show you the picture. He's going to show you the actual items. But you probably can see or cannot see those things. The next thing is we need to make some measurements. We have to collect some data. And, we just can't put your finger and say, okay, it looks like 2 inches or so. Can't do that. So you've got to have some correct measurements. So there are a bunch of instruments, and this shows the pressure and flow. Some of them you already know. You start with a manometer, which on the left side. You got to be at least 40 years old or 50 years old to know and how to use the manometer, because today's generation would use digital manometer, which is diametrically opposite. But remember, even those instruments needs to be calibrated. And only way you're going to be able to calibrate that is use the old-fashioned manometer. So we bring manometers as well as we bring the digital instruments for measuring the pressures and flows, particularly pressures, delta P also. The one on the top left side middle is inclined tube manometer that is used for draft measurements. If you look at the furnace pressures, they are not going to be in terms of 2 inches water column or 2 psi, but they're going to be in terms of 0.5 inch water column or 0.2 inch water column. And you need these inclined tubes, top and bottom. So either one, there are 2 different types of things. There are digital instruments available, but again, you need to have proper calibration means to do that. And inclined tube manometers are used for low pressures also. The one in the middle top is the orifice meters. I'm sure each one of you know that. The other one on the side is the flow meter, which people use for measuring the gas flows, and this is particularly used for measuring the atmosphere, such as DX gas or RX gas. So these are glass tube of flow meters also. At the bottom is the T-dot tube, which is used for measuring the static pressure differential, which gives us some idea about the velocity of the gases, and we can measure the velocity of the gases by measuring the delta P and size of the pipe, so on and so forth. So these are the pressure and flow type of instrument. Next one, Sachin. Next, Sachin. Yeah. The other one, which is really important, is temperature and flue gases. The left side on the top is a flue gas monitoring instrument, which allows us to measure two important parameters. One is the temperature of the flue gases, and the other one is the oxygen. In addition to that, there are other things that this meter will measure, which is called combustible CO, or in some cases, nitrogen oxides, and other combustible gases. There are many different types of instruments. The one we bring in for assessment, it's got to be the oxygen measurements and temperature measurements. The next to that on the top is a whole bunch of thermocouples, which you have seen many times. Next to that is a multimeter, which is used for measuring multivolts or high voltages, and multivolts are important if you're using the thermocouples. Starting from the left side bottom is a infrared instrument, which allows us to sight the thing at the light beam, laser beam or infrared beam, and measure the actual spot temperature. Next to that is another temperature measurement device, which we connect to thermocouples. And next to that is a really important and interesting device, is the actual photograph or the thermograph to take a look at a surface and find out a hot spot and cold spot. For years and years, we could not afford to have this kind of instruments because they were very expensive, $20,000, $30,000 or so. Now they are coming to a reasonable level, somewhere between $5,000 to $10,000, but they're extremely important for measuring temperature profile, air leaks, so on and so forth. Next slide, Sachin.
Right. Arvind,
Yeah.
I think maybe let me present next three, 4 slides. That way you will get some break and then you come back again. Is that okay? Yes. All right. Okay. So, so these are basically different equipment, diagnostic equipment for temperature and flue gas measurement. And we are going to ship this equipment to Southville plant well at least 3-4 days in advance. And during implant training, you will actually get to use this equipment in the plant, and you will actually collect data and you will use this equipment in person. So on next slide, now data analysis. So for data analysis, we are going to make things easy for you. What we are going to do is we are going to use process heating, assessment, and survey tool. We call it FAST tool. And so this tool actually helps you to estimate annual energy use as well as annual energy cost for different process heating equipment. So during implant trainings, we are going to create a FAST file for roughly 4 or 5 process heating equipment. And so based on data we are going to enter in FAST tool, it will actually show us estimated annual energy cost, annual energy use for different furnaces in this plant. Then this tool will also help us to perform detailed heat balance analysis. So different types of losses, how actually, whatever energy we are consuming there, whatever fuels we are burning, total natural gas we are burning, how that energy is actually used. So that Sankey diagram, heat energy for heating steel or whatever material we are heating or melting, and then different types of losses like opening losses, wall losses, exhaust gas losses. So this tool, FAST tool, will help us to perform that detailed heat balance analysis also. Now, after that heat balance analysis, we will perform what-if analysis for possible energy reduction and efficiency improvements. So in this FAST tool, we'll have current conditions as well as modified conditions. And so a comparison between current conditions and modified conditions will give us what-if analysis. And then also this tool and our analysis will help us in obtaining information on energy saving methods and identifying additional resources. So this is just a screen, FAST 3.0 process heating assessment survey tool. If you look at this tool, and we are going to give you demo on FAST tool at the end of this webinar. But if you look at, you have different calculators for easy and fast calculations. Then you have plant or equipment information. This is where you create equipment entries. So you add, let's say there are 4 or 5 process heating equipment in your plant. You enter high-level data for those equipment in this particular tab right here, and then each individual process heating equipment, you will be able to do heat balance analysis using this third tab on right-hand side, top right-hand side. And then you will be able to create different types of reports using report button, and then import and export functionality. So those functionalities right now, if you are using Microsoft Access after 2010, you won't be able to use these 2 functions. But eventually, maybe this year or next year, we are planning to completely update this tool. We will have newer version of FAST tool, so we will fix those issues. But mostly for our implant training analysis, we will use these 4 different buttons, and those are important functionalities. And now access and requirements. So FAST 3.0 tool is actually no longer available on DOE website because we are trying to replace. We are basically replacing it with process heating modular tool. Process heating modular tool is available on DOE website, but it's going through basically alpha and beta testing. There are a couple of issues with that tool, and we are going to fix those tools in next couple of months, next maybe 2-3 months. So basically, we have plan to kind of, in short, we have plan to update this FAST tool and make it more modern and even much easy to use. But FAST 3.0 is still, through an analysis point of view, through implant training point of view, you will not face any issues. So and I think we shared this particular link to you, and if you download this tool, you will get a zip folder, and if you unzip that folder, you will be able to install FAST 3.0 on your computer. Okay, so and definitely we'll discuss more on FAST tool later. But I think most important part today's webinar, we need to understand how this heat balance analysis is done. So if you look at FAST tool, at the heart of FAST tool, you have this kind of Sankey diagram. And if you look at, this is your furnace heat input, whatever natural gas or electricity, total electricity you are consuming, or maybe in some cases you are using coal or coke, fuel oils. So that's your total furnace heat input. And then if you subtract basically exhaust heat loss in the form of flue gases, exhaust gas loss, if you subtract that from your gross fuel input, you get available heat. So now that available heat is available for you to do useful work. And this is right here. This is basically theoretical heat energy needed to either heat or melt whatever material you are dealing with. So that's like heat needed, a theoretical amount of heat energy needed to do useful work. But what happens is, if you're using, let's say, 400, 500 MMBTU per pound, in reality, you are consuming almost 2,000, 2,500 MMBTU per pound. I'm giving you example of aluminum, for example, aluminum melting. So you just need 400 MMBTU per pound to melt 1 pound of aluminum. But in reality, you end up consuming 2,000 to 2,500 MMBTU, depending upon type of an age of melting furnace. So all that if you subtract, roughly 1,500 MMBTUs is actually lost. And what kind of losses are there? So you have opening losses. So if you have fixed openings or variable openings to your furnace, you're losing heat energy due to radiation and convection through those openings, and that's basically opening loss. Then you also have cooling water loss as well as conveyor losses. So that's also a kind of heat loss you need to deal with. Then if your operation is batch kind of operation, you basically start furnace, you run furnace, you stop it for a few hours, maybe 8, 9, 10 hours or something like that. And depending upon size of furnace, then you are basically dealing with heat storage losses, because when you start that furnace, you are also heating walls or mass of all that furnace. So you are losing heat energy there too. For continuous furnaces, this storage loss is not that relevant. Then you also have wall losses, and then you also have flue gas losses. So basically, FAST tool helps us to identify different losses, and it also helps us quantify how much it lost, different type of loss. Basically, it helps you create this kind of Sankey diagram. Here is a typical heat balance for a walking beam furnace, and this is walking beam steel reheating furnace, and you can see. So good thing is, so this along with Sankey diagram, FAST tool also provides you this kind of pie chart. So 61.2% of total heat energy is actually going here to basically reheat your steel material. But then you are losing almost 6% in the form of water cooling losses, as this is walking beam furnace, so you are actually using water cooling. And then there are wall losses, roughly 3%, and then you have flue gas losses, almost 30%. And then energy use, so theoretical energy use is 0.68 MMBTU per ton. So this much is needed, 0.68 MMBTU per ton. But in reality, you end up consuming 1 to 1.6 MMBTU per ton. So like because of these losses, you basically consuming more heat energy. Again, now heat supply, demand, and losses. And in this diagram, what we are showing, this is again Sankey diagram. So along with Sankey diagram, what FAST tool is doing, it's also giving you before and after energy savings analysis. So you can see in right next to these arrows, there are two numbers. For example, flue gas losses in this case. This is reheat furnace in steel plant and flue gas losses. So if you look at their current operation, flue gas losses are almost 10 MMBTU per hour. So basically 1.8 MMBTU per hour is needed to reheat the steel material. That's useful heat. But then when you are doing that, you are almost losing 10 MMBTU per hour. So that's current operation. Now modified is basically what if analysis. What if we install recuperator, or we basically recover or recycle waste heat from these flue gases and use it for some useful purpose. So in that case, what's happening is now you are going from 10 MMBTU per hour to 3.6 MMBTU. So basically our point is, along with this Sankey diagram, different types of losses, this tool is also giving you current and modified operation. So I think this is where I think, Arvind, you should come back, because your experience is important. So Arvind, this is slide number 26, process heating system revisited.
Yeah, I'm here, Sachin. Yeah, no problem. So we go back and look at this diagram, and we will use that as a guide for discussing the energy saving potential, or the kind of things that one can do in saving energy. Next slide, Sachin. So we start with the number one, which is called load or charge preheating. Obviously, there are many different things one can do, and some of them can be applied in your case or in anyone else's case, and not all of them can be applied. So this is sort of, a menu, and it's applicable for your own situation. So we start with the big ones, whether it's electric arc furnace or it is reheat furnace. Number one is the hot charging of the load. If we can hot charge the material, or we could preheat the material, for example, scrap preheating in case of arc furnaces, or hot charging directly from the caster to the furnace itself, or even preheating it by external source is one of the most commonly used and recommended method. The final load temperature. You may be bringing the slabs or billets out at 2250. The billet temperature measurements is extremely difficult because of the presence of slags and stuff like that. Why 2250? Why not 2200? Well, the proof is pudding is going to come in the rolling mill. If you break the roll, you're in trouble, and because you reduce the temperature too low, or the amps are going very high. So some people have actual controls of the final temperature by using the feedback from the rolling area also. Moisture content. Certainly you don't have any moisture going into the reheat furnaces, but there may be some going into arc furnaces. And what I mean by moisture, it doesn't necessarily mean water. It could be hydrocarbon vapors or oils or those kind of things also. Reduce the load reaction, so that's reducing the oxidation. It helps us in two ways. Obviously, it reduces the material losses, but at the same time, it improves the heating process also. So reducing the load reactions by using methods such as scale-free heating would be another example. Avoid partial loading. This is one of the most important things. Furnace is designed, like in your case, 110 tons an hour, and you run it only at 60 tons an hour. You pay pretty heavy penalty for that. And actually, the FAST program can help you to see what kind of penalty you pay if you run the furnace at partial loading or so. Then the next one area is the material handling. This is more or less used for heat treating kind of operations, where you reduce the fixture trays and basket weights. For example, in case of batch annealing furnaces, how do you reduce the inner cover weight, or those kind of things? Return the house fixtures and conveyors. Very few of these are applicable to your plants directly at this point. The next one is the combustion system itself. A whole bunch of things people can take a look at it. Number one is the air-fuel ratio control. Making sure that the burners are operating properly, they have proper air and proper fuel going in there, and the ultimate test, it's going to be the oxygen coming out of the stack itself. Oftentimes what happens is that people will call the burner suppliers or somebody and say, hey, check my burner's control ratio. They'll adjust the burners perfectly. The problem is that what you put it in doesn't matter. What goes out is what it matters. So now we got to take a look at what's going on and adjust the ratios accordingly. Change from constant air to ratio burners. Number three, which is really important, is use of preheated combustion air. Most people try to do that as much as possible, but not enough. With the gas prices down, people kind of take a look at it and say, why do I spend money in recuperator? For more than one reasons, and we will discuss those in the classroom itself. Outdoor, being in Saukville, Wisconsin, unfortunately, probably the day when we are there, the temperature is going to be 10 degrees Fahrenheit, high temperature. We close the building, we have a lot of makeup air going through there, and then we suck the air from the plant itself as a combustion air. no good. It creates problems. So we'll take a look at those kind of things. In some cases, using turbine exhaust gases for combustion air, this is something we are taking a look at it very, very rigorously and see what can we do. Use of alternate fuel, not an option for you. Direct gas firing to replace the supplemental electric heating, not an option for you. Oh yes, you do. Particularly in the arc furnaces, if you can get by using oxy-fuel burners or carbon injections or oxygen injections, those kind of things. Electricity is very expensive compared to the gas prices today, so that's another area we ask people to take a look at it. Oxygen enrichment or using oxygen or partial oxygen higher than 21% is another area we can take a look at it. Next slide, Sachin. Flue gas and exhaust gases, there are a whole bunch of things that can be done, and we don't have enough time. I'm already at 1:50 p.m. So I'm just going to say reducing the excess air, combustion air preheating, load preheating, makeup air heating. These are a whole bunch of things that we will discuss. And the number 10, use of waste heat for absorption, cooling, or steam is another area. Electric power generation is another area. So there are a whole bunch of things, and out of these 12, maybe 3 or 4 are practically applicable to a steel plant like yours. Next one is the wall losses. Previous slide, Sachin, for a second. Okay, again, reduce the wall losses, reduce the wind velocity, shut down the furnace. These are some of the things. But the only thing that can be done is while you're rebuilding the furnace, use the lighter and better insulation. Next. Sachin, next. Opening losses. This is one of the major areas where people have no idea how much heat they are losing by direct radiation. But it's amazing how much heat goes out on the radiation. And we'll talk about that in the... by the way, for each of these areas, the FAST tool can help you estimate how much energy you can save by taking actions on any one of these items, or most of the items, let's put it that way. So that's another advantage of using FAST, that you know whether it's worthwhile doing something or not. The next one is control system, auxiliary systems, and there are other methods of reducing energy losses. So these are some of the things that we will discuss in detail, and also analyze these to see whether you can use any one of these, and if you use, how much energy can actually be saved. Next slide, Sachin. This gives you a ballpark number. Don't have to spend time on that, because we will actually look at your own furnaces and see what you can save in each one of these areas. In your case, this is what we figured out at this point, is that you have melting furnaces where energy is used, refining is used, ladle and tundish heating, not much energy used in continuous casting. Actually, it's a negative energy use, which we take away a lot of heat. Reheating obviously is one big one. Not much energy used in cold rolling, lots of energy used in annealing and heat treating, and some of them may be in the finishing operation. So we will mark up each one of these, and then between David and Terry, we have made some decisions on what kind of equipment we are going to use for making measurements. Next slide, Sachin. So this is your plant. I don't have to tell you that, but what we are going to look at is melt shop, rolling mill, and the processing area. So these are the 3 areas we are going to look at. Next one. Sachin? Yeah. A reheat furnace, as far as I can tell, and I was there, I believe, in 2003 or something. 118 million BTU per hour, about 110 tons per hour capacity. Things have changed since then. We'll find out. And the fuel is natural gas. by far the largest energy user. Next slide. This one is the finishing area plant layout. David has helped us marking up this, but we'll take a look at it when we get there and see what furnaces are and where they are located. But it seems there's a whole bunch of distance between number 42 and number 5, so it's going to be a long walk, I guess, yeah. So we have to be careful in seeing when and where we schedule these data collection things. Next slide, Sachin. Continuous annealing furnaces look like there are a whole bunch of radiant tubes in there, and we will take a look at these also and see what's going on in these furnaces. Because there are so many radiant tubes, the data collection, it'd be interesting to see how we can collect the data, how fast, and what representative radiant tubes or other data we can get. On day one, we are actually going to go out in the plant and take a look at each one of these furnaces to see where and how we can collect the data, if it's practical to collect the data. If it's not practical, what is the backdoor side to get some of the numbers, those kind of things. So we will take a look at this when we actually are present. You can see here 17.6 million BTU per hour versus 118 million BTU. So it's a huge difference in energy use and efficiency also. Next, Sachin. Next, Sachin. Okay, this one looks like a batch furnace, annealing furnace again. I assume it's radiant tube fired, and we'll take a look at this furnace also, number 5. Next, Sachin. Then again, number 2 furnace, each of them are like 10 million BTU per hour, large and yet relatively small. Next, Sachin. 41 is another furnace. We'll take a look at that. Look like it is a fiber insulation with radiant tubes, I can see. So we can take a look at these furnaces. So 1 direct fired furnace, 3 or 4 indirect fired furnaces. So I have promised you a lot in terms of what we will do and what we can do. Now Sachin is going to give you actual demonstration of FAST 3.0. Sachin, you got 32 minutes.
All right, perfect. So what we'll do, Arvind, we'll use maybe 15 minutes and then maybe 15 to 20 minutes, and then we will go for question and answers. I'm sure participants, they have probably at least few questions. Okay, so once you install FAST 3.0 on your computer, you will see this kind of shortcut on your desktop. So FAST 3.0, once you double click on that, you will see that previous screen. I think I already showed you that screen. So okay, so you get basically 2 options when you start FAST 3.0. You get option 1 is select heating system. So heating system, either you will be dealing with electrotechnology or you are most likely dealing with fuel-fired systems. So electrotechnology is basically electric arc furnace, infrared, induction melting furnaces. So whatever electrotechnologies are there, those are covered under electrotechnology section of FAST tool. And then fuel-fired furnaces, like reheat furnace, wherever you are using natural gas or fuel oil or coal, basically go with fuel-fired furnace. You click OK. Then again, that's that second question, select units for your analysis, data analysis. So unit point of view, you basically do 2 options: US units, imperial units, or you basically go with international units. In this case, let's go ahead with US units. So once you answer those 2 questions, now you see this main screen, FAST 3.0 main screen. So you have calculators, you have plant or equipment information, then you have furnace analysis, heat balance button right here, and then you have different reports. import plant information and export plant information. So at the same time, along with these buttons, top left corner, you have other options. So under information, you have unit converter. If you click on that, it shows you unit converter. So area, density, energy. So different types of units you will be able to convert from BTU to joules or kilowatt hour to BTUs, those kind of things. Then you also have CO2 emission factors. So for different fuels, whatever emission factors are there, so those basically pounds of CO2 per MMBTU, that information is also there. Then you have user manual. So user manual is basically step-by-step a guidebook how to use FAST 3.0 tool. And then as Arvind mentioned during his presentation, you also have data collection forms available inside this tool. We are planning to share with you Excel version of data collection form, but inside this tool you have a PDF version of data collection forms. So what you can do is, before you go out in the plant to collect data specific to different furnaces, what you can do is you can print data collection form and take it with you, because whatever data you are going to collect using this data collection form, so same data is actually used inside FAST tool to do heat balance analysis. So kind of we're trying to make things easy for you. So with that, now if you look at calculators, if you click on calculator, there are 4 different calculators available inside FAST tool. So number 1 is energy equivalency calculator. If you are switching from fuel-fired process heating equipment to electricity-driven process heating equipment, you want to see what kind of difference is there, basically energy-wise, what kind of savings possible. So you can use this calculator to do that analysis. Or at the same time, if you are switching from electrotechnology to fuel-fired system, in that case also you can use this calculator. It's basically easy to use calculator without spending a lot of time. Next one is efficiency improvement calculator. Efficiency improvement calculator is basically if you, let's say, reheat furnace. If you know at present 6% oxygen in exhaust gases, flue gas temperature is, let's say, 600 degrees Fahrenheit, and then excess. So this calculator actually helps you kind of quantify how much fuel savings possible if you go from 6% oxygen level in exhaust gas to 2% oxygen, or if you go from flue gas temperature 600 degree Fahrenheit to 250 degree Fahrenheit. So very easy to use, handy calculator. Same thing with oxygen enrichment calculator. If you want to enrich combustion air with oxygen rather than just 21% oxygen, if you want to go for maybe 100% oxygen or 80% oxygen, you can actually use this calculator and see what kind of fuel savings possible. And then last one is flow calculations, energy use. So if you are using orifice meters in your plant, and you have data regarding orifice meter, you are collecting pressure before after orifice meter, and you know what kind of gas you are dealing with, then you can use this calculator to figure out energy flow and flow basically in standard cubic feet per hour for whatever gas you are dealing with there. So these are easy to use 4 calculators, and then now after this particular button, if you go for plant or equipment information, you will see we are asking a little bit high level information to start actual analysis, data analysis. So before you go to furnace analysis or heat balance analysis, make sure you first go here under plant or equipment information tab, and then you enter all different process heating equipment and data associated with those equipment in this particular tab, and then go to furnace analysis heat balance tab. because without that, if you directly go for heat balance, you will not see your equipment under this tab. So you first need to create those process heating equipment in this second tab, plant or equipment information tab. And I'm going to show you where exactly and how exactly you are going to create equipment files inside FastTool. So once you click that plant information or equipment information tab, you will see there are three basic tabs, kind of sub-tabs. One is general information, second is energy source related information, and then third one is furnace information. So general information is company name, plant description, then basically what currency you would like to use. You can use different currencies. We used actually this tool in different countries, so China, Brazil, and there even India. So we were able to use this particular part to quantify energy cost savings in local currency. So in this case, we will just go ahead and use US dollar, and then plant address, and then contact information. Then click next. You will go to energy source tab, and energy source tab, whatever energy sources you are using in this plant, we make sure we enter heating value related data, and then unit cost of those different sources. So by default, you will see you have electricity, natural gas, steam, but let's say your fuel is missing in this list. What you need to do is create new energy source. You click on new energy source, and then you enter, is this energy source is like fuel or electricity or steam. You select that, and then you enter name for your energy source, then heating value, whatever unit you want to use, BTU per cubic feet, BTU per gallon, BTU per pound, and then you enter cost, unit cost data, like in unit for your unit cost, US dollars per MMBTU or US dollar per ton, and then you basically kind of save. And then with that, then you will see in this drop-down menu, you whatever new energy source you created, you will see that in this drop-down menu. So let's say we entered a Coke. So now you select Coke in under energy source, and then you enter heating value in BTU per pound, and then unit cost per unit, like dollars per ton. And then if you click save, it will basically save. Let's say it's I know it's basically, let's say just $8 per, let's say $80 per ton. And if you just save, you will create new energy source in this list. So heating value is there, and dollar per ton value is also there. So that's how you enter new energy sources. So one, you added general information regarding your plant. Second, you added information regarding different energy sources. Now next one is, and this is most important one, furnace information. So now let's say I'm just going to show you one example. This is actually steel plant, test steel plant somewhere in Ohio, and for this plant we already have different types of energy sources there. And now in third tab right here we have furnace information. So for this plant we already added different equipment. So we have electric arc furnace, then we have ladle heater 1, ladle heater number 2, reheat furnace, steam boiler, turn dish heater 2, water heater. Now this is just example. Now in Saukville, Wisconsin plant, when you will start creating plant file for that specific plant, you will not have anything here under furnace information, blank, nothing. So what you would require to do is click on new furnace, and then enter information regarding new furnace in different tabs. So again, let me go back here. So once you click on new furnace, this new window will pop out, and now here you need to enter furnace name, furnace description, now operating hours information, then heat zones. Let me actually close this, and let's open existing furnace so that you'll be able to see all different tabs. So operating hours. So you enter operating hours for this particular reheat furnace. This is walking beam reheat furnace. Now next one is heat zones. So in this walking beam reheat furnace, there are 5 different zones. Heat zone bottom, heat zone top, preheat zone, soak zone bottom, soak zone top. Again, we are adding high level information regarding reheat furnace in this particular tab. So operating hours, then data regarding heat zones, and what kind of data we need to enter in heat zones for different heat zones. So for example, heating zone bottom. So what we need to enter is what kind of fuel is used in that zone, then how many burners in that zone. In this case, there are 6 burners in that zone, and then what's like total burner rating for that zone. So if you add burner ratings for those 6 burners, MMBTU per hour, what's like total MMBTU per hour for that specific zone, and that's 40 MMBTU per hour. Now next 2 fields are percent of rated capacity used and then percent loading factor. Now if you do not understand what these terms definition, if you want to understand, if you want to know definition for these terms, here is actually question mark. So if you click on this help, it will actually list all different terms we using in that specific calculator, whatever screen you are right now on, and then kind of definition. So term and then description. So for example, percent of rated capacity used. What that means is given number that represent percentage of the rated heat input firing rate used in the zone. This is percentage of the rated value given in zone burner rating for all burners above. And then percent loading factor is, this is percent of operating hours or time the burners are fired or used. So basically, if you have any question regarding any of these fields, there is actually help available. So that's it. In this zone, we have 6 burners. Total burner rating, zone burner rating for all burners is 40 MMBTU per hour, 60% of rated capacity used, and then 50% of time those burners are actually running. And electric heating, steam heating is not needed. We don't need to worry about these 2 fields. That's it. Same thing with other zones also. So we enter data for heating zone top, preheat zone, soak zone bottom, soak zone top. And once that is done, then we enter data regarding auxiliary equipment. So in this case, there are total 4 pumps associated with this walking beam reheat furnace, and then 4 fans or blowers are associated with this walking beam reheat furnace, and then there are 5 other motors. And what we need to know is basically total connected power, horsepower for those motors, and then duty cycle and rated capacity. And then tool quantifies total energy used by those auxiliary equipment. And then last tab is notes. So whatever notes you would like to enter regarding this particular equipment, you enter all those notes here. In this case, I'm saying this is for a walking beam furnace, data collected from the supplier, proposal, and the operator input. Done. So that is actually reheat furnace. So what we did here, we actually, let me quickly go back again. So what we did here, we went in plant or equipment information, we collected general information for this particular plant, we collected energy source information for this particular plant, and then we basically added all these different process heating equipment, and then we also entered data specific to, for example, reheat furnace or ladle heater 1, ladle heater number 2. So we entered we entered operating hours information, then heating zone related information, and then auxiliary equipment information, and then we also added nodes. Once that part is done, we are done with this particular tab. So plant or equipment information tab is complete. Now we are good to go to the next tab. Now let's click on furnace analysis heat balance tab. Now once you click that tab, you will see the screen, and tool will ask you what specific plant, and then you will see your plant. So for example, on first day of our training, we will create a plant file for Southville, Wisconsin plant, and we will see that plant in this drop down menu. Now let's select, in this case, test steel plant, and then once you select that, you will see process heating equipment associated with that steel plant. So see, all these equipments are visible because we already created kind of high level information for all these equipment in plant information tab. Now let's select the heat furnace, because we want to do heat balance analysis on our reheat furnace. Now once you click that, once you select reheat furnace, you will see total 9 different tabs. As Arvind actually went over all the different types of losses. So for each loss, now we have separate calculator. So first one is theoretical amount of heat energy needed to heat or melt your charged material. So this is load or charged material. So amount, here you are seeing heat required, BTU per hour needed. This is basically theoretical heat energy needed to heat or melt your charged material. And then next one is fixture or tray losses. Then you have atmosphere losses, then opening losses, wall losses, water cooling losses. Then you have heat storage losses, particularly for batch kind of furnaces. And then you have flue gas losses. This is very important. Most cases you will be dealing with flue gas losses. And then you have other losses. Other losses basically exposed hot parts, extended hot surfaces, and then whatever loss we haven't accounted using these different types of losses. You can just enter some data here, BTU per hour. So that's it. So basically, idea here is you use data collection form to collect whatever data needed to do these calculations, and you come back and then you start entering this data one by one. So you have current operation, you have modified operation, you enter data, and then you basically quantify different types of losses. So very quickly, let's look at, for example, what kind of data is needed to quantify theoretical heat energy needed to for example, heat steel or melt aluminum or reheat steel material. So if you look at what we are asking here, select type of material. Is it solid material? Is it liquid material or gaseous material? Let's say we want to do calculations for steel material. So that is actually solid. So from drop down menu, we are going to select, let's say it's carbon steel. So carbon steel, and then we are asking you charge feed rate, pounds per hour. So in most cases, I think if you look at for whatever furnace we will be dealing with at Southville plant, we will get this information. Production, maybe annual production data, or maybe monthly production data, or maybe we will also, if we are lucky, we may get pounds per hour data also. So we just enter that. In this case, it's 6,000 pounds per hour carbon steel. Water content as charged. So if there is moisture or ice or whatever water content, in this case, let's say it's 0%. Water content as discharge. Now again, if you do not understand any of these terms, you can always click on this question mark, and you will see explanation for all these different terms. So water content as charged, water content as discharge, initial temperature. Now initial temperature is initial temperature of carbon steel. So let's say initial temperature is 70 degree Fahrenheit. This is cold charging. This is reheat furnace. Let's say it's going in at 70 degree Fahrenheit. Water discharge temperature. Let's not worry about it. Discharge temperature. Now discharge temperature is discharge temperature for this carbon steel. Let's say it is actually, we are discharging it at 1000 degree Fahrenheit. I don't know exact temperature there, but let's just say 1000 degree Fahrenheit. And charge melted. in this case, we are not melting anything. We are just reheating carbon steel from 70 degree Fahrenheit to 1000 degree Fahrenheit. Then charge reacted. This is basically oxidation, as Arvind actually mentioned during his presentation, that in reheat furnace we may need to deal with oxidation, particularly top layers lose some material due to oxidation. So you can actually enter, if you have data regarding that, how much charge is actually reacting, and so how much basically oxidation taking place. Is it 0.5%, 0.8%, or 1%? And then if you enter this information, then you need to also enter heat of reaction. So that means BTU per pound, because oxidation is, let's say, exothermic reaction. So in that case, you are going to generate some heat energy. So BTU per pound when 1% of steel is, let's say, reacted. So you enter all that data here, and then additional heat required, and that's it. Now in this case, what I did, I only used 6,000 pounds per hour, and then our initial temperature is 70, our discharge temperature is 1000, and this tool is giving me how much heat energy, theoretically, how much heat energy is needed to reheat carbon steel from 70 to 1000 degree Fahrenheit, and it is actually 837,000 BTU per hour. That's it. And now this is current conditions, right? And once we enter data for all different types of losses in this current condition, current operation form, then we can actually switch to modified part. So to do that, there is actually a button called enter or edit modified data. Now you can actually modify basically what if analysis. What if, so in this case, let's say 6,000 pounds per hour. Then let's say rather than cold charging, let's say let's actually these billets, let's say, going in at 200 degree Fahrenheit. So you basically say 200 degree Fahrenheit here, and then discharge temperature, let's keep it 1000. So what happened here, by just going from 70 degree Fahrenheit to 200 degree Fahrenheit, you are actually reducing energy consumption from 837,000 BTU per hour to 720,000 BTU per hour. So that's basically that kind of analysis we'll be doing in this plant during our in-plant training. So current condition, modified operation, what if analysis, and then difference between these two numbers, kind of energy savings. So now if you click on furnace summary button, you will see that similar kind of Sankey diagram is generated. This is basically useful output. So this is like theoretical amount of heat energy needed, 837,000 BTU per hour, and current numbers are in blue color, modified condition or modified operation are in red color. These are different types of losses, and what it's showing, what it's saying is basically thermal efficiency of this furnace is just 11 or 12%, and under modified condition you are going from 11.3% to roughly 15.6%. This tool also gives you BTU per pound. This is basically these numbers are energy intensity numbers. So current condition, you are 1,238 BTU per pound. This much amount of heat energy you are consuming per pound material processed, and under modified conditions you are consuming less energy. And now you can use BTU per pound numbers to benchmark your reheat furnace with other reheat furnaces. There is actually a lot of reports out there. They provide a reheat furnace energy intensity numbers, and now you can compare. In these numbers, you can compare with state of the art or average energy intensity numbers for reheating operation. So once you complete heat balance analysis for reheat furnace, you close this, and again you go back and you do something similar for ladle heater 1 or tundish heater 2, electric arc furnace. And then once your analysis is done, you basically close, and now you are ready for reports button. Now reports, there are 4 different types of reports. Plant summary report, then furnace analysis report, furnace summary report, and then input data report. Plant summary report, if you click on that, it shows so basically plant level information, whatever information you provided, location and currency and all that information. Then summary of energy sources used. Then this report, plant summary report, also shows you this kind of pie chart. This pie chart is showing how energy is used, energy cost distribution by equipment. So in this case, electric arc furnace is consuming basically 62% of energy cost is associated with electric arc furnace. Then 14.1% is associated with a reheat furnace, and then remaining equipment. Then same information in table format. Now you can use this report to submit, after your energy assessment. Now, if you want to get funding for implementing energy efficiency opportunities, you can actually use this report to convince your upper management. So now that is plant summary report. Now, if you look at furnace analysis report, let's just look at only reheat furnace report. So this is furnace analysis report for reheat furnace. What it's showing is how heat energy is used in that reheat furnace. So water losses, wall losses, different types of losses. If you click next, so this is basically current condition heat consumption, and this is basically gross heat consumption data. So what it's showing is for this reheat furnace, almost 40% of heat energy is lost in the form of flue gases. Then 27% heat loss is water losses, wall losses. So different types of losses are actually shown here. And then modified condition. And then in the end, you will see a comparison between current and modified operation. So flue gas losses, current condition, and then flue gas losses, modified condition. And difference between those two kind of energy savings. And then in the end, whatever notes we added when we actually did energy assessment on individual equipment. So that's pretty much. So sorry, we don't have a lot of time to go over a lot of details during this webinar, but we just wanted to give you kind of just high level kind of flavor so that you are prepared for actual implant training. So Arvind, you have any additional comments at this point?
No, we don't. I only say that most of the people going to attend would have access to the actual schedule. I think we already send them, or we will somehow they will know what's happening on day 1, what's happening on day 2. If you if you have it handy, I can talk about it for 2 minutes. If not, then we will request David and Terry to inform the people on what's going on. So it's already 2:29. So let them say whether we want to spend a couple of more minutes or not.
Right. Okay, let me actually make sure Terry and Dave are not on mute. Okay. Hi, Terry, you there?
Hi, yes, I'm here.
All right. So how you would like us to proceed?
If you wanna spend another 5 minutes going through the agenda, that would be fine. And for just to excuse those who have another meeting or conflict, to go ahead with that. We did include the agenda with the main meeting invitation. So if you want to go ahead, spend a few minutes on that, that would be fine.
Okay. So what we'll do is we'll just spend no more than 3 minutes. That will be total 4 days. Number 1, day 1, we are going to have some safety. Then we were going to have the presentations in the classroom, and then there's going to be explanation of instruments, actual demonstrations of instruments and diagnostic equipment. Then we are going to talk about the data collection forms so that people understand which term means what. And we will go into the plant, look at each of these equipment, would not make any major effort in collecting data or anything like that, but just to find out what data should be collected from where, and if there's any need to do something, we can make that decision and talk to the plant people about doing that, so drilling a hole or this or that or that. Next morning we come here and we all go to the actual plant and we start working on collecting data for each of these equipment that we have. Come back in the afternoon, start using the FAST tool, entering the data in the FAST tool, and I think we'll have a full day doing that. If there's any kind of questions or anything. Day 3 is the day when we do a lot of analysis work. We discuss the FAST results. We meet in a conference room or somewhere, and we ask people about their opinion on what should be, suggested way. Normally, we, depending on number of people, we may divide them into 3 teams, and there will be one team leader who will be responsible for managing the process itself. And then at the end of day 3, hopefully we have a list which people have discussed and come up with the energy saving measures. And you guys really don't have much to do on the night of 3rd, but Sachin and I are going to have a busy evening, because this is when we prepare the actual presentation for the next day. And we discuss that in front of plant management, and we show them what we have come up with, and conclude the whole project or the activities by about noon time or so. Hopefully the weather cooperates and there is no snow. Cold we can handle probably, but this is the general outline of what we are going to do. Any comments, Terry, from your side?
No, if this is an updated version, if I can just get a copy of it, that would be great, and I'll include that in the meeting invitation.
Sachin?
Yes, that's correct. Yes, I'm actually going to send Arvind's presentation, today's presentation, and then updated version of this short presentation to you, Terry, and then you can go ahead and share with all participants.
Sounds good.
So Terry, how many people we have now registered or are expected to be there?
Originally, I think we had close to 35 invited, and I've had a couple of people that have notified me today that they won't be able to make it. So I'll take a count of the people that have accepted and declined and forward that on to you.
Okay,
right.
Great.
And then what we'll do, Terry, as we discussed, last day, at least wrap-up meeting, last day of implant training, we will kind of maybe try to create a webinar so that if people somehow, if they are somehow not able to participate, still they will be able to join us remotely. But generally, webinar is tough, particularly from plant environment, like because of noise and everything. So yeah.
2659500.
Right. So I think with that, this ends our webinar. Thank you so much for joining our today's webinar. And as I mentioned, we will share our slides from today's webinar via email in the next day or two. And then Arvind, thank you again. Thank you for your time and all this very useful information and your experience, sharing your experience with us. Terry and Dave, thank you for joining webinar today's webinar.
Thank you, everybody. We'll see you in a couple of weeks.
Thank you.
Thank you.
Thank you.